So let me know, come by, talk to me if you have any questions at all. Now, you're going to see that this chapter, you kind of already know most of this stuff. It's kind of obvious to you from the previous two chapters and from experimental, when you did stuff like this in experiments. And so this is going to be redox titrations. Of course, you can do titrations with a redox reaction instead of a normal acid-base reaction, right? Technically, an acid-base reaction could be considered in some cases a redox-style reaction. So they're very similar in most cases. It's just there's a lot of things we never really talked about in acid-based titrations. They're going to show up and become an issue in redox titrations. Okay, they're incredibly common worldwide in industry because they're just really, really readily available, easy to set up, very reliable processes. Redox titrations, do you need the definitions or are you good? Okay. Okay, then I'm going to skip those so we can actually get through some material that's useful for you. You can use them in basically any science that looks at compounds that are oxidizable or reducible, right? And so that's almost all the sciences except for things like astronomy, where you can't get your samples usually. But redox titrations were used on the moon samples that they were able to bring back. So if you can bring back the samples, or you can have a probe do the titrations for you. The Mars lander, that had redox titrations, was how it did most of its composition analysis, in case you're wondering. These are the major attributes of redox titrations, and so typically one analyte per titration you're going to look at. The accuracy and precision are quite excellent, actually, because we can measure electrical differences very accurately, and you can use very, very low concentrations to get very accurate measurements, right? The cost is extremely low. The biggest cost in a redox titration is time. Okay, it's the time of the people that you're using to do the titration, and you can train a layperson to do titrations pretty well in like a week of training. They don't need to know what they're doing. They just need to know when this goes to that, add this much, right? Like the actual titrations themselves are quite simple. It's very suitable for low resource environments. You don't have to buy an ICP-MS, that's $100,000. You don't have to buy a fancy spectrometer that's $20,000 plus dollars. You can make up a solution usually for $100, if even that, and that would last for most labs a few days. Okay, and then you could do literally thousands of samples off of a few $100s in equipment. Time is usually the most expensive part. These are some different oxidizing and reducing agents that you might see in redox titrations. The list of them can be quite exhaustive, and I'm not going to go over that, but there it is. Okay, if you're trying to look for a redox titrating agent, those are good ones. So we got to talk about the shape. Okay, you're used to titration curves, right? Looks very similar to this, right? The only problem with the shape for titration curves for redox reactions is that you don't have very, very, very standard species that are going to be on both sides of this. So when you were doing this before, in reality, one of the species that you were doing for acid-base titrations was always water. Okay? And so it standardized all of those titration curves and reactions and equilibriums around that species, right? This is not going to have that. You're going to have two species and they're interplaying, and so you are going to have two sides of this titration curve that will look different. Okay, it will not be nice symmetric, unless you have very unusual circumstances. So let's consider this titration here. This is sort of the example I'm going to use for everything that we talked about for a while. Okay, and so right here you have a burette, right? And you're going to be adding. And so you're going to be adding cesium 4 plus to a solution of iron 2 plus. This needs to be an HClO. Do you remember when we dissolved the iron in the lab? This is very similar to that, right? HClO is just doesn't produce chlorine gas versus HCl. Okay, it's to keep it dissolved and oxidized like that. This right here is going to be your electrode setup. And so we have a calomel reference electrode right here. And over here we have a nice platinum wire, so you can just directly measure this solution. Okay. And then we'll have a stirring bar to keep everything mixed. Keep in mind this will not automatically be the exact value. It takes time. Now, this is what this titration curve looks like. This is actual experimental one in case you're wondering. This is the potential right here. This is the voltage versus the calomel electrode right there, the SCE. This one right here is going to be your volume you put in of the titrant. Okay. And so what we'll see here is we'll again get an equivalence point, right? And that's going to be your inflection point. And so that equivalence point is always, right? Where you've consumed all of one species. Okay. And so we'll have consumed all of the iron 2+, right? Okay. That makes sense? Okay. Now, when we do that, what we're going to see is the potential here, that equation looks like this. And so we have this platinum versus the calomel, right? The difference between those electrodes. And that platinum electrode right here is going to be measuring the iron 3+ versus the iron 2+. The iron 3+ being the product of this titration, the iron 2+ being the reactant, the start of it, right? Now, if we get to 1/2 VE, what always ends up being true there? Mm-hmm. That is true. That was absolutely true. But that is for pH, right? We're not looking at pH here. You'll notice this is not pH, right? And so what's going to be true there is the other thing that was true in the acid-base systems. So if you got to 1/2 the equivalence point, then you've used up half of your reactant, didn't you? And so at this point right here, we're going to be 1/2 and 1/2 between the two species of irons. Okay. Okay. And so there's sort of three major things we need to start off with, and that is identifying the titrant reactant and the indicator half reaction. So we need to get the half reactions and the overall reaction, because these half reactions are going to be interplaying, and we're going to end up measuring these. Think of it like this, okay? You have here your reference electrode, right? And then on the other side of that reference electrode, you have two competing reactions. You have two competing half cells, okay? You have a half cell that is the iron and iron 3+, right? So 3+ and 2+ iron, okay? And then you have a half cell that is the cesium. So you have the cesium half reaction, right? That is the 4+ versus the 3+. So 3+ on top. And so those are the two reactions, the half reactions that are taking place in this, right? That gives you your overall reaction. That's going to give you your titration curve. When you're in this portion right here, that's when you're going to have the iron, right? Any cesium that comes in is going to get used up. Okay? And so that's the half reaction for the iron, the reactant that you have in the deal that you measure. This stuff right here, everything after this is excess of that titrant, right? And so that is going to end up being the half reaction for the cesium. Okay? And so what you have is you have a titration where the titration curve is one half reaction that then passes over to the other. Okay? At this interface right here, you're going to see that interplay between the two. Right? Is that making some sense? Okay. I want you to have that like as an overall framework when you look at these things. So you got to recognize here that the initial potential before any titrant is added, this can be measured, but we cannot actually predict this. Okay? To predict the rest of the titration curve, you have to divide the redox titration curve calculations into before the equivalence point, just like an acid-base system, at the equivalence point, and then after the equivalence point. And so it's the same sort of breakup as the acid-base systems, but the reasoning is very similar. But you got to remember that in this case, we're going to have voltage differences for them. We're going to have Nernst equation differences for them. And so we didn't normally see that stuff when we were looking at the pH curves, right? Now, because we're doing these in the voltage differences, not pH levels, right? We're seeing that more. We're understanding it more, at least, hopefully. Right. And so this right here is going to be your titration reaction. Are you okay with that? And then half reaction, of course, is just the electron transfers. Don't forget the electron amount number here, the number of electrons being transferred, is very, very important for these titrations because it is going to completely change how this titration curve looks and how these, the ratio. It's not like acid-base systems where you always did 1H plus at time, period. Okay. And then the next one was harder to take off, right? The electrons, 2 electrons come off if 2 electrons come off. And they're going to come off pretty easy in comparison. Okay. There is a harder time getting the second off. It's just not that big a difference. So the E naughts here, these are the E naughts. Those are the standard conditions, 1 molar, etc., for these half reactions right there. You'll notice they're both positive values right now. And that's because we've represented both of these half reactions as our standard reduction potentials, right? And so these are going to be in 1 molar HClO4, and that's going to keep everything dissolved. Okay, now, the titrant CE4 plus is going to be completely consumed up to this point right here, right? So whatever amount we put in for that, it's going to be gone by the time we actually have a measurement. Okay, that's actually what we're waiting for when we're waiting for that to settle, in case you wonder. That's part of what we're waiting for. And so it's going to have excess Fe2 plus, and so we can just take the Fe2 plus versus Fe3 plus concentration, plug it into the Nernst equation. Right there's our standard one. That's the value. Notice it's a 1 electron, so the N is just 1 and don't need to care about it. That's the SCE probe right there, that minus 0.241. We can actually sum these terms up if we're going to be doing a bunch of these measurements, which we usually are. And so we can just take the SCE probe and our E naught, and they're both constants, right? Now, you can flip this if you ever wanted or needed to. For whatever reason, it would just flip the sign, okay? Now, that's just that equation right there, the same potential equation. Let's look at. Okay, so when you have 1/2 VE, when your volume equals 1/2 VE, remember your species for the Fe3 plus and the Fe2 plus are going to be equal. Okay, what's your species of the CE4 plus? That's the one we're dripping in, yeah, titrant. That's 0. We don't have any of that. It'll be consumed all the way still because we're not at equivalence point yet, right? And then the CE3 plus will be 100%. Everything's in CE3 plus, okay? Because, again, it's all going to be converted in this case. Okay, so if we look at this, well, we have the same over the same, right? The log of 1 is 0, and so that entire term drops out as 0, and so we get this right here at the 1/2 equivalence point. And so your pK equals pH? Kinda. Kinda, right? Because at 1/2 equivalence point, we have the voltage, which is the standard voltages of the system, isn't it? Okay? Because our concentrations cancel out. So that's just going to give you your E naught of your analyte, the thing you're measuring. And then it's going to give you minus that reference electrode because we're never starting at 0 for our references, right? We're always starting at something. Okay. Getting a 0 reference electrode, you should double check if you ever do try to do that. You probably don't have 0. It'd be very unusual. You'd have to very, very difficultly assign that. That'd be a lot of work. Now, exactly enough CE4 plus will have been added at the equivalence point. And so when we get to the equivalence point, what we're going to see is that we have converted all of the Fe2 plus to Fe3 plus. We'll have the exact same amount of Ce4 plus added as there is Fe2 plus, right? And so that's our equivalence point right there. And so what we're going to see here is that we're going to have an interplay between that Ce3 plus equilibrium and the Fe3 plus equilibrium. How much of that would go backwards, right? And so we're going to have very tiny amounts of Ce4 plus and Fe2 plus at equilibrium. Both half reactions are going to be at equilibrium at that platinum electrode. And so we can actually just use both of those reactions to describe the cell voltage. So here we have that E plus, right? And that would be that platinum electrode. And so they're both going to have to be the same voltage because they're the same system. And they're going to be equal to that E plus, right? And so what we're going to do there is we're just going to set both of those up. So 2E plus, that's going to equal those two added together, right? Because they equal E plus, so they have to be 2E plus if we add them together. Okay? And that's just the Nernst equation for both of the products there. Does that make sense? Okay. Okay. And so what we're going to see here is, again, we take these two values. You always want to go ahead and add those two up right off the bat because that'll make your life easy because they're constants, right? And then you're going to take care of these right here. Now we're going to merge these. And so what we're going to see is this is minus this log. This is minus that log as well. And so we can add those together. If we add logs, that multiplies the stuff inside, right? Okay, minusing logs divides. And so we get the Fe2 plus, Ce3 plus on top, and then the bottoms are on the bottom. And that gives us that combined thing. Now, don't worry too much. That will actually simplify in this case, though you need to understand this part in case you ever end up with a situation where you got to put like a 2 times, 3 times, that sort of thing. Again, it simplifies still. You just need that 2 times, 3 times. Okay. And so at the equivalence point, we're going to have that Fe2 plus that has to equal the Ce4 plus, right? Well, if they both react together and produce product, then the products also have to be equal, don't they? Because it's a 1-to-1 ratio. Okay. This is where that would come in, like, I make 2 of these for every one of those. Okay. You're going to see it'll still simplify very nicely, though. Okay. And so what we see is we just plug those in so we can convert, variable exchange, either one. It doesn't really matter. Because what it'll do is still cancel, right? So if we take Ce4 plus right there and put in Fe2 plus, well, that's just going to cancel right there, isn't it? Okay. And if we do the same on the other side, we're just going to get canceling out. So anytime we do a variable exchange there, we're going to cancel everything. Okay. That will all go to 1, a log of 1, 0. So that's gone. We'll summarize this into a shorter formula in just a bit, okay? But I need you to understand how to do it. This is what you finally get, so you divide by 2, because we added those together. This is going to give you your E plus, and so we plug that in for our E plus, we subtract off the calomel, and that's going to give us that 0.99, okay? And that would be our voltage right there. See how it's very close to 1? And so this is actually the simplified formula if you go ahead and leave everything in variables, okay? And so what you get here is you get our E plus is actually going to be equivalent to the N. Remember, N is the number of electrons, right? And that's where I was talking about that number of electrons is important. We need to keep those in. And so that's going to be N times its E naught, that standard reduction potential, plus N times the E naught of 2. Notice that's the same in there. Okay. And then this is divided by N plus N2. Okay. And that's going to be equivalent to the entire Nernst equation stuff. You can just plug that stuff in. Much easier, much faster. If you have that formula, hint, hint, on perhaps a sheet that you get to bring to exams, it would be highly advisable to write that down. Not that I don't give you the Nernst equation, but it takes a lot more work, right? Okay. And so at equivalence point, everything's been converted, right? And so we just have products. After the equivalence point, well, that's where we're going to add more titrant, but we don't have any more iron to convert, right? So we're just directly adding more cesium 4+, and then we're going to have the cesium 3+ that was converted from the iron. And so you're going to make a concentration cell there that you're adding more concentration to until you hit that voltage of the maximum concentration difference right here. Okay. And so what's going to end up happening is this going to look like this. And so we just directly have the Nernst equation for the cesium 3+ versus cesium 4+ concentrations. Just a nice concentration cell. And then minus the Calvin, because we're referencing versus Calvin, the SCE. Okay. Did that all make sense? Okay. Now, let's say we add twice as much, 2 times the VE. What is that going to look like? Well, if we add 2 times the VE, what we're going to see is that we're going to end up in like another half VE sort of point, but that's the double VE, right? And so what we're going to have is an equal amount of the CE3+ as the CE4+. And so again, we're going to get that voltage there. Okay? So that's going to be what it's going to sort of climb up. And it's going to start leveling off around that point. It will not necessarily ever hit a like ceiling per se. It'll keep going sort of a linear relationship there, because you're going to make a concentration cell, though you will get vastly diminishing returns, and so it will tail off, okay, as your concentration of the CE4+ completely overwhelms the CE3+. But it has a much longer tail than a traditional pH equation, okay? Okay, redox buffers. Just like acid-base systems, you can also make redox systems that have buffering. This is actually really common in like swamps. Swamps have really great buffering capacity for redox systems, okay? Because it has a very large amount of like methyl groups, methylized groups, that can do a lot of buffering. Again, this is going to resist change, right, in the electric potential when oxidants and reactants are added. And so here we have an example of that. This is going to be I hate this guy's name. I have a lot of problem. I normally have heard it called as a pH diagram in every text I've ever seen except for this one. And this one is correct. I've looked it up. And I have never seen that before, which is quite something. But poor bakes is how I keep pronouncing it, and I'm almost certain it's wrong. But I just cannot get myself to make French. French is not happening. Diagram. Okay. If you call it a PE-pH diagram or predominance diagram, that's what most people will call it. Okay. And so what it's going to be is it's going to be the pH versus the potential, the PE, as it were. And so this is going to be these two graphed apart like this. And then you'll have the interchange between the species drawn out like this. Okay. And so, for example, as your pH goes up, you'll have more hydroxide in the solution, right? And so your lead 2+, that's free and dissolved in the solution, is going to go to lead hydroxide as you increase that pH. Okay. If you go to more acidic conditions, on the other hand, it's going to slide on over and it's going to make your lead 2+. You heard of Flint, Michigan? Flint, Michigan. Okay. That's what happened there. They were apparently right about on this line right here and then slid across. Okay. If you have this right here, potential goes down a bit. You can actually have your lead phosphates and then your lead hydroxide, but notice this is the 4, this is the 2. Okay. This right here is then solid lead. So if you get enough electrons in that system, you're going to actually plate out lead, right? And you convert all the different salts to the solid metal lead. Okay? Does that make sense? Okay, let's have you try this out, okay? And commit to an answer here. Just the first one. Let's go on it. You'll get a chance in homework to try. Let me know when you got it or get stuck. Okay. Okay. So we have before at equivalence point, after. Right? This is not 1/2 equivalence point. Would have been really convenient, right? And so we need to set up this right here, which is going to be our E equals the standard Nernst equation, difference of iron, right? Okay. And so, and then that's the system we got set up. We plug these in. This is going to be that difference between for the 18 milliliters, where we have 18 milliliters that have been used up. And so 18 out of our 25 will have been used up and converted to the other form, right? And of that 25, we have 7 remaining that's going to be in that form. Now, notice that you can just use those ratios directly in this. So if we just do 18 of the 25 gets used up, 7 of the 25 remaining, that would be the ratio, right? It'd be the whatever percentage that is, right? But the 25s would cancel because we're putting on one on top of each other. So we can just 7, 18. Okay. And so we plug that in and we get 0.55. Was it okay? Okay. At equivalence point, this is what we have to do right here. And so at the 25, we're going to have that equivalence point. We just use that equation. That's going to end up being 0.99 volts because that equation is entirely independent from concentrations. We had no concentrations in that equation whatsoever. So the answer we did whenever we did that part, same answer. As long as you're looking at that same reaction, same answer. Okay? If it's at equivalence point, that's what it is. Because you've used up all the species. Now, at 31.5 milliliters, we're going to be past the equivalence point, right? And so past the equivalence point, we're just looking at adding more CE4 plus to the existing CE3 plus, right? And so what we're going to get here is it's going to end up being a ratio of those concentrations. That's a 25 to 6.5 ratio. Okay. And so that's all we need to plug in for here. The 25 we've added to the equivalence point versus the 6.5 we added past it. And that will give us that value right there. Any questions? Yeah, it's all kind of just somewhat obvious results of what we looked at before. Now, the shapes of these redox titration curves, they will change. The equivalence point does not actually have to be in the middle of this right here. It's not, see how that's not in the middle? It is the inflection point, this being the inflection right here, right? And what we're looking at is we're changing over the half cells each time, okay? So up to this, we're the analyte. After the equivalence point, we're the titrant, okay? All right. So when the titration stoichiometry is 1-to-1, your titration curve will be symmetric. When it's not 1-to-1 ratio, when you have a 3-to-1, 2-to-1, this is a 2-to-1, by the way, stoichiometry, you're going to see a titration curve like this, and you'll see that this is about 2 times what this is. Okay? And so that's what we're seeing there. We can have an uneven number. Now, in pH chemistry, acid-base chemistry, because of the definition of it and how it worked, we were always looking at 1-to-1 ratios when we were talking about those curves, right? Because you always deprotonate one thing at a time and then the next, right? In these, they happen on top of each other. Okay, so how do we find endpoints? Well, we're going to use indicators just like the pH acid-base world, okay? They have almost all the same rules as the pH indicators because realistically speaking, those indicators we were looking at were, basically doing the same stuff. There wasn't a huge difference, right? One was binding H+, now we're binding an Fe3+. Not a huge difference. It changes the color when we do it, okay? You can plug these indicators in. They're going to be redox agents, of course. And so you can plug them into the Nernst equation here. And it's going to have the exact same form as before. Again, remember, it's going to be the oxidized on bottom, reduced on top here. Now, in this case right here, notice we'll have a pale blue going to red. Now, when do you see an indicator change, by the way? Do you remember from the acid-base world? Yeah, it's the 10 times. So if you have 10 times one form versus the other, that's going to be where you'll start seeing a change. Okay? And so anytime we have a 10 times difference, that's when we see a change. Notice because it's in the Nernst equation, this being a 10 times difference, right, is one unit of that Nernst equation, right? It's going to be a log of 10, which is 1, or a log of 1/10, which is -1, right? And so you'll always get this relationship right here, which is the E naught plus or minus that Nernst constant right here, divided by the number of electrons there, okay? And so that's what you see for your color change in terms of volts. Now, if your system is very sensitive and you need to keep this in mind whenever you're setting up these indicator systems. Okay, it's actually quite important, right? Because notice not all indicator systems are going to cover the same range of volts, right? It's going to depend on the number of electrons. Okay? And where it changes, the color is going to depend on the E naught, right? So if you need something that changes at 7 volts, then you need to pick something where the E naught is around 7, right? Pretty close to 7. Okay, so this right here is going to be your color changing E naught right here, where it would change over, and you'd start seeing that difference. These would be your colors. These would be indicators. These are commonly used indicators that work quite well, okay? And so if you're trying to select an indicator, these would be the one. Notice that some of these are the same indicators we used in the pH world. For example, methylene blue. Still here. Okay. Hey, welcome back, old friend, right? Um, so the larger the difference in your standard potential between the titrant and the analyte, the greater the break in the titration curve at the equivalence point. A redox indicator will give satisfactory visual endpoint when the difference in formal potentials of the analyte and titrant is equal to or greater than 0.4 volts. Okay, that's that sort of range where you need for your indicator light color change to be something you can register. If the difference is smaller at that equivalence point than the 0.4 volts, it's very unlikely you're going to be able to see it. Okay. Fluorescent molecules actually will glow when exposed to light. So a fluorescent redox indicator is going to be a compound that loses or gains fluorescence where it undergoes the oxidation to its reduced state. So right here we've oxidized this to reduced state, and we're going to lose or gain that fluorescence depending on the molecule. Okay, and there can be they're very nice for a multitude of reasons. Heavily used in like biochemistry. Um, so some of the fluorescent indicators are going to be things like quantum dots. You can actually make those fairly easy. N-phenyl anthracylate acid can enable redox titrations and titrations as low as 1 micromolar analytes. Keep in mind, micromolar, 1/1,000th of a molar, that's actually really, really small concentrations for something you could do a titration for. This is the starch iodine complex, a very, very common redox indicator because it's very cheap and it's fairly easy to make. Okay. You can get this for way less money than most indicators. Most indicators are like $50 for a milligram. This is, of course, like kilograms for tens of dollars, right? So the structure of iodine and amylose actually remains an open question. People are not entirely sure of what that structure is. The theoretical interpretation of your visible absorption spectrum suggests that the iodine amylose actually exists as these forms right here, which is an I2 bonded to an I5 minus bonded to an I2. And so the units with the II bond length is 0.31 nanometers. And it looks like something like that probably, where it has like the iodines packed in between the amylose structure. Okay. Anyways. Okay. Now, when you do these, sometimes the analyte oxidation state needs to be adjusted prior to titration. Not all of your iron molecules may have been in a 2+ form, right? Not all of them may have been in a 3+ form. You need to adjust them into the form you want. And so the pre-adjustment, usually called pre-oxidation or pre-reduction, depending on what you're doing, this must be quantitative, okay? And the reason it has to be quantitative, if you put in a lot of excess stuff that can oxidize or reduce this back, then that's going to show up in your titration, right? Because you're going to make this, and then you're just going to oxidize or reduce it right back, aren't you? Even if it's selective. So the excess pre-adjustment reagent has to be eliminated, so it does not interfere in the subsequent titration. It's very important for that steps. These are some of the different pre-oxidations you'd see. Nitric acid, for example, which we've used quite extensively. Remember what Will went in to do last semester with the nitric acid, with the copper? Mm-hmm. That was a nitric acid pre-oxidation. Okay. And so the nitrogen oxides are going to be removed by boiling the solution, and that's why you boil that solution at the end. Anyways, I'm going to skip the rest of these. There's nothing super. This is a good one that's in basic solutions, which is peroxide. And so you boil it again, and that will destroy all the remaining peroxide. Let's talk about some pre-reduction. Now, I'm gonna be honest. All mercury things are basically verboten now and very difficult to get outside of industry or government. Government can get them still, but they're very difficult for most people to buy. So if you see anything mercury anymore, know that you're probably not going to be using that if you go to industry. Okay, and if you go into academia, you're definitely not using it. Now, stannous chloride, chromase chloride, sulfur dioxide, hydrogen sulfide. These are mild ones, and you can expel them by boiling in acidic solution. So they're very commonly used, actually. Now, this is actually some different techniques you can use for pre-reduction. I don't think there's anything I can particularly add to this other than mercury is toxic, and you can't buy the mercury stuff anymore. It's very expensive because nobody wants to produce it. So, but yeah. So let's look at an example. I think that's usually our best bet. Now, we have here nitrate in drinking water. The EPA limit for nitrate, as of the publication of this book, which is fairly recent, is less than 10 parts per million. This number has been changing lately, by the way, in different countries, and so it's kind of a moving target nowadays. A lot of places actually way undercut the allowed in their drinking water because that target keeps moving around. So classical nitrate assays, this uses metallic cadmium to reduce the nitrate to NO2 minus. That would be a pre-reduction step, of course. However, the CD is toxic. It's going to create a hazardous waste, and you'll make quite a bit of it, actually, because you're going to have to pre-reduce your entire solution, right? And so there is a more environmental friendly nitrogen assay. We change out the CD with a biological reducing agent, and that biological reducing agent is NADH, as in the same thing as like supplement in your body. Yes, that one. And so that is much, much better for the environment, of course, and very similar to biology, isn't it? And so we do need to use a nitrate reductase usually to speed this reaction up. We need to keep this around pH 7 or else we will cause the enzyme to not function properly. But that goes quite quickly with the enzyme. Okay, not something we could have done back in the day when they used this. Because isolating enzymes, packaging them, and sending them, and all that stuff was not something that was easy to do. This would have been thousands of dollars to get that enzyme, and it would have not lasted. So, spectrophotometric assay is then used to detect that nitrate. You can use spectrometers, of course, to detect wavelength changes and differences. And so oftentimes that's a better way than to try to see it visually. And you can see it in places where you can't see light visibly, of course. This right here is some oxidizing reducing agents that are used in bioanalyses. These are very common ones. You'll notice right here, this is trisphosphine right here. You'll see this quite a bit, actually. So these techniques are incredibly common in biology. And the interesting thing is that I find interesting actually is that like somebody sets them up and figures it out and standardizes it. And then biology has a very, very good like published technique to I'm selling you all this stuff and now you use it pipeline. That is really fast, faster than any other industry I've seen. And so what you'll see is that the biologists will be doing these redox titrations, and they don't even know what a redox titration is. Like they're just doing the procedure, and they have absolutely no idea that that's what they're doing. And it would be most of the people doing these that I've seen. Okay, so This is bottom-up proteomics, a very popular method to analyze proteins. So after the proteins are extracted from the cell, you'd have a next step, which is going to be your bottom-up methods. This is going to be used to unravel your 3D structure of your proteins so you can more easily analyze them. And so you'll use high concentrations of denaturants that disrupt the covalent interactions within the protein. Also, the covalent ones, which is disulfide, is a covalent one. Oftentimes, what you're going to have is a combination of effects holding a protein together, right? And you're aware of them, I would think, because I think you've taken biochemistry. But in case anybody forgot, we have salt bridges, right? We have hydrophobic interactions. We have hydrophilic interactions, which are hydrogen bonding. And then we would have disulfide linkages, right? And those would be like our really major ones that we have to concentrate on. And so these high concentrations or denaturants, those can help us disrupt those non-covalent interactions, right? Like, for example, salt bridges, you can salt proteins out by putting too much salt in solution, okay? Our 3D structure that's held together by cysteines, on the other hand, well, this requires an oxidation reduction, right? And so we can pre-reduce this to separate all those, can't we? So we're using a pre-production. And so this is actually that reduction. This is going to be with thiol reagents. And so here's our disulfide bridge. That's the pre-reducing agent. And we get our split disulfide bridge. Okay. Now, these reductants that contain phosphorus will react to form thiols and phosphine oxide. And so this will, again, split up that disulfide linkage, but we'll instead get a phosphate here instead of the disulfide, other disulfide, not protein disulfide. Okay. Now, we do need to prevent recombination because those disulfide bonds do typically form because they're fairly stable. Okay, so you'd get some degree of recombination depending on stability, of course. And so the thiol product is usually going to be stabilized by alkylating it. We put some sort of alkane group on there so that it can't recombine. And so iodoacetaminide works very well. This is just an SN2 reaction, if you remember that from organic chemistry, where this is going to attack and this is going to be a leaving. Okay. And so potassium permanganate, very popular oxidizing agent, very strong oxidizing reagent, a lot of side reactions if you're not careful with this. Somewhat difficult to store. So very strong oxidizing agent, intense violet color. Have you used this or seen this before? Like a... Yeah, we have a lot of problems in small labs like ours that don't have a lot of students going through with potassium permanganate because it does destroy over time due to oxygen and light. And so it's somewhat hard to make batches that are small enough and store them. You have to make them fresh all the time. Labs with lab techs use it a lot because it breaks down over time. And so you can just dump it out. It actually is quite nice. So potassium permanganate actually reduces down to Mn2+. This is colorless and strongly acidic solutions. And so that would be the breakdown in acidic solutions right there. MnO2, if you've ever used this, you probably saw some brown specks in the bottle. And these are the brown specks. Or it may have turned cloudy and brown. If so, it's mostly broken down. And it's made MnO2, which is a solid and a brown color. Now, this one here is fairly unusual to see because most people don't use this in alkaline solutions or keep this in alkaline solutions. But in alkaline solutions, you can actually get the MnO4 going to the 2- form. And so this actually gives you a voltage difference and is a half reaction and everything else. And so you can actually use potassium permanganate as its own indicator in acidic solutions. So if you have a redox reaction using one of these and it's an acidic solution, you can actually use it as its own indicator, which is kind of cool. And so this right here is some different analytical applications of our permanganate titrations. As I said before, very strong oxidizing agent, very useful oxidizing agent, quite widely used for many applications, right? And as you can see here, really, really common, actually. This is like the standard redox reactions and titrations you might see, especially in a general chemistry lab, would use this. Now, potassium permanganate is not a primary standard because you're going to almost always have traces of MnO2 that are present. The distilled water will contain enough organic impurities even to reduce some of the MnO4 minus to the MnO2. So even your professor making it, very likely that distilled water they were using already did something. Okay. And then you get into the fresh versus old stuff, and it's changing the entire time. So to prepare a 0.02 molarity stock solution, you dissolve this in distilled water, you boil it and filter it through a sintered glass filter. You then store the reagent in a dark glass bottle, typically an amber bottle, and you'd want to minimize light exposure as much as possible. Aqueous potassium permanganate is unstable. This is by virtue of this reaction right here. And so this is why that permanganate, even if you do everything correct and you put it in the fridge, will still over time get MnO2. Okay. But if you put it in the fridge, you limit its light exposure, you can prolong that. Okay. Because again, it is a reaction, it does require energy. So again, in the absence of MnO2, Mn2 plus, heat, light, acids, bases, potassium permanganate is going to be standardized by titration with sodium oxalate. Remember sodium oxalate we used? Very common standardizing agent for redox agents. Okay. You can also use iron. Iron also works extremely well, though you do need to keep it dry. Otherwise, over time, it will rust. And we have a lot of problems with the dang iron rusting all the time and not using it up fast enough. So, cesium 4 plus as an oxidizing titrant. Cesium 4 plus will bind anions, which are these ones right here. ClO4 minus, SO4 2 minus, NO3 minus, and Cl minus. So these would be the various different formal potentials in those different solutions. Remember how we made this big huff about we're using HClO4 and it's 1 molarity. That's why. It's because they have different formal potentials because they will bind those ions. Okay. Again, it's cesium 4 plus. 4 plus is a lot charge, right? And it's a fairly large-ish metal, right? I mean, it's 4 plus, so it's smaller than you think. But the cesium 4 plus is yellow. The cesium 3 plus is colorless. The color change is not distinct. It takes a long time. And so you are going to have a lot of trouble seeing that. That's why it's not its own indicator. The ferroin and other substituted phenanthroline redox indicators are going to be well suited to titrations with cesium 4 plus. Cesium 4 plus can be used in place of potassium permanganate in most procedures. There are some where it will not be suitable, but most procedures it can. Now, the primary standard grade ammonium hexanitratoacetate. I murdered that. My tongue is just. I've had troubles all morning. Anyways, this is the formula. This can be dissolved in 1 molarity H2SO4. Then we can use that directly. And so that's actually quite nice. The oxidizing strength of the cesium 4 plus is going to be greater in the chlorate versus the nitric acid. But these solutions are going to undergo slow photochemical decomposition, which will concomitate oxidation of the water. And so cesium 4 plus in H2SO4 is stable indefinitely. The reduction potential of 1.44 volts is going to be great enough to oxidize the H2O to O2, but even still, it is stable indefinitely. Solutions in HCl are going to be unstable, and this because the 4 plus is going to oxidize the chloride into Cl2. And remember how we had problems with that the one titration we did last semester. Anyways, these are the different ones right there. These are adequate for preparing titrants that are subsequently going to be standardized with our primary standards. Okay, so this one's potassium dichromate. You have probably seen that. Maybe not used it, but you've probably seen it. A number of other places. It shows up quite often. This is actually a primary standard for redox titrations, and its solutions are stable. It's one of the more common ones to use. In acid, you'll have an orange dichromate ion. It's a powerful oxidant. It's going to be reduced to chromic ion, and this is the chromic ion right here. Now, the chromic ion here, this is not very harmful to the environment. In fact, you need some of this in your diet, so it's not a major issue. However, there's a couple problems with this. Number one, it is food. So bacteria has this stuff all the time. I've had to throw out all of my solutions I've ever had to throw out for this is because it gets this cloudy bacterial growth in the middle. That's why every single one of these solutions I've had to throw out. Okay. The hexachromium is the one that's toxic and oftentimes gets misunderstood as being this, which is the 6 plus. This is not as strong of an oxidant as the Ce4 plus potassium permanganate. It will be converted into yellow chromate ion. The oxidation power of that is essentially nil. And so that's this reaction right here. The indicators like diphenylamine, sulfonic acid, and diphenylbenzidine sulfonic acid are going to be used to find the dichromate endpoints. And those are those pictures on the right. Primarily used for determination of iron 2 plus, or you can also indirectly use it with iron 2 plus to measure something that will oxidize the iron 2 plus. Okay, and so you oxidize the iron 2 plus, and then you do a titration of the iron 2 plus to find out how much got oxidized. Because remember, the irons are nice standards; they are pretty easy to standardize things with, right? Reactions can be moderate with platinum and calomel electrodes. Now, one of the major things that you're going to see in terms of environmental and EPA standards chemistry is that drinking water industrial waste streams will oftentimes be partially characterized and regulated based on their carbon content and oxygen demand. And part of that's because life in those streams requires oxygen, and the carbon changes that oxygen levels. But part of it also is that carbon's fairly sensitive to a lot of these oxidation changes. It has its own major species that you would see at different pH and oxidation levels. Okay, and you can follow that quite nicely, and it helps you monitor systems then. Now, inorganic carbon, which is IC, is the abbreviation. This is going to correspond to carbonate and bicarbonate in water. Do you remember bicarbonate? Okay. And so an important parameter in boiler water where carbonic acid can induce corrosion. IC is being measured by measuring the absorption of infrared light of CO2 that's liberated when the sample is acidified to a pH that's less than 2 and sparged with gas. After inorganic carbon is removed, the total organic carbon, which is TOC, this is the number you would typically see in environmental reports, by the way. TOC is the CO2 that's produced by oxidizing the remaining organic matter. So you completely oxidize everything in a pre-oxidation, and that's going to give you your CO2, which you then measure. Okay. This, by the way, is how you can convert the organic carbon into CO2. You can plenty of O2 in 700 to 1000 degrees Celsius temperatures. Notice that's basically kiln temperatures, right? Same sort of thing we were talking about before. That was why we did that. Remember where we did the procedure last semester where we were taking the iron and we were getting rid of the filter paper? So we heated it to about 900-ish. This was why. Because if you have organic carbon, it's going to convert to CO2. Metal catalysts can really, really help this reaction go faster. In that we couldn't add a metal catalyst. At least no additional metal catalyst. So the total carbon, that's TC, is going to be defined as TOC, total organic carbon, and the inorganic carbon added together, of course. Commercial instruments will using combustion can analyze the IC and TOC of a less than 10 milliliter sample in 3 to 5 minutes. They have detection limits of about 50 nanograms of carbon per milliliter of the sample, which is quite excellent, actually. These can analyze samples that are up to 0.02 grams of carbon per milliliter. Suitable for analysis of water for IC and TOC ranging in the drinking water, wastewater, that sort of thing. Okay. If you have like sludge, plant matter, that sort of stuff, this is not going to be suitable as is. You would have to do some pre-treatment. Okay. How much time do I have? 7 minutes? About done. Okay. So when we're looking at industry, there's a number of different things we have to quantify and look at. Basically because somebody dumped too much of it in one environment and overwhelmed that environment's capacity to absorb it, right? And so now we're aware that that's an issue, which is something you can do on almost anything that's possible. Okay, you can literally put too much heat in environments, right? It's called heat waste. But some of these are very important to monitor more closely. And so, for example, free radical oxidation methods, these are going to have detection limits of less than 5 nanogram of carbon per milliliter. These are commonly used in things like the pharmaceutical and electronics industry for drinking water analysis. Color plate 14 is going to be this one right here is an instrument in which the K2S2O8 is an acid. This is exposed to ultraviolet radiation. This generates a sulfite radical. This will then oxidize the organic matter to CO2. So that's what you're actually seeing there. You can actually have other instruments generating sulfite radicals by heating the K2S2O8 to 100 degrees Celsius. But then you're at 100 degrees Celsius. The total oxygen demand is going to tell us how much O2 is required for complete combustion of the pollutants in the waste stream. So if you want to completely combust everything CO2, get rid of all of those pollutants in the waste stream, that's going to be TOD. So the volume of N2 with a known quantity of O2 mixed in the sample in complete combustion is going to be carried out. It's going to be carried out typically in a catalyst to make it faster, so you don't have to wait as long, at 900 degrees Celsius. Notice 900 degrees Celsius is very common for these things because you don't want to get up past 1,000. Okay. So the chemical oxygen demand, which is COD, This is going to be defined as the O2 that's chemically equivalent to the C2O7 consumed in the oxidation of pollutants. I don't think there's anything in here that's particularly demanding. Is there anything that doesn't make sense in this material so far? Yeah, I'm gonna see if there's anything that's a little bit more difficult. This is one of those things where sometimes I really have to freaking wonder about my field and go, why? Why? Did you need to do that? No. No. Like adsorb versus absorb? Come on. I get it, but come on. So iodometry, iodimetry. And so iodimetry, reducing agent is titrated with iodine. This produces iodide. And so that makes sense. Yes, iodide, yeah. Iodometry, oxidizing agent is added to excess I minus, and this produces iodine, which is then going to be titrated with thiosulfate solution and make the your titration. So the molecular iodine is actually not very soluble in water, in case you're wondering. This actually takes a process to dissolve if you ever need to make iodine water. What you can do, though, is you can put something like I minus. You typically need something alongside it, though, or heat to heat it up. And then the I3 minus is going to be more soluble in solution if you ever need to do this. You will need excess of the I minus to get all of the iodine dissolved, though, or at least the vast majority. The reason you want to do this, though, is because in iodimetry, the starch can be added at the beginning of this titration. This is why this is so different. And so your first drop of excess I3 minus after the equivalence point will cause that solution to turn that dark blue color. Keep in mind that it may not look like blue to you because it's in a solution and it has other colors. Okay. Iodometry, the starch should not be added until immediately before the equivalence point. Remember titration last time? That was iodometry. Otherwise, your iodine is going to remain bound to your starch particles and it can't interact in the solution. And so you can detect the visual by fading of the iodine in solution. This is the fading of the iodine right here, by the way. See how it goes from like a nice like wine color, and then it goes to more like a yellowish color. And then you'd put in your starch indicator. And that would give you your blue, which mixed with yellow. Now, the reason you want to use iodine and iodine is so popular is because you prepare the I3 minus by dissolving the I2 in excess Ki, right? The I2 is actually sublimed. So you can take gaseous I2, which is quite easily, you can just heat it, it'll go into the gaseous form. And then you can have it land on something that's cold, like cold glass, right? And you can then make the solid. And so you can make an extremely pure sample. There's not a lot of things that would have similar boiling and melt and freezing points, sublimation points, as iodine. However, it's definitely pure enough. We don't use it very often as a primary standard, and this is a measuring problem. So can you measure it? Yes, but it would take a very specialized equipment to measure it. Okay. And the reason for that is if you just measure this on a balance out in the open at room temperature, you're going to actually have some of this that will actually sublime. It'll go into gas and that will not be captured. It will disappear, right? And so the approximate amount is going to be rapidly weighed. You would then make a solution, and then you would standardize it with Na2S2O3. Acidic solutions of I3 minus are actually unstable. This is because the excess I minus will slowly oxidize in the air, and you'll get this right here. And so you'll get this increasing, changing I3 minus concentration, which is kind of fun and cool because usually you make this stuff and it breaks down, right? this one's the reverse. You get more of it if you leave it there. So the funny part is you can like make up these solutions and then you can just put a little bit of acid and then take the acid back out. And then you can like neutralize the acid, with some HCl. And then you can actually like restandardize them. But it's not usually worth it. It's a lot for nothing. But if you don't have any solution made and you need it real quick, hint, hint. I've had to do that. In neutral solutions, oxidations can be insignificant in the absence of heat, light, and metal ions. And so they store fairly easy. At pH of greater than 11, the triiodide is actually going to disproportionate to hypoiodous acid, iodate, and iodide. And so it'll break apart the triiodide, actually. This is a really good way to make this. So we're gonna. Oh, I'm past time, aren't I? Okay. I'll finish up next time. We'll probably just talk about these parts right here. We'll start up on 59.